Started. All right. So welcome to the last lecture for dynamics, where we're looking at work energy principle and linear momentum and angular momentum stuff. The third exam problem is going to be work energy. So super important. So keep, make note of the stuff that we go through for work energy, and also the first problem that we do today. For linear and angular momentum in rigid bodies, I am not going to give you guys an exam problem, but you will have one homework problem, all right? And homework 9 has been posted today, and it's due next Thursday. And what I'll do is, instead of making the take home live on Thursday night, I'll make it live on Friday night. That way is for anyone who has, you guys always need a little bit of time to get your last homeworks in, and then I'll post the solutions as well for homework 7, 8, 9, and I'll post the exam basically at the same time on Friday night. All right, so you guys, the exam will go live at Friday night, and you'll have the weekend and Monday, and then all of Tuesday to get it in, and we'll make it due on Tuesday night, if that sounds all right. Okay. All right, so principle of work and energy, just to recall what we had looked at when we had looked at particle. Can you guys hear me and see the screen okay? All good, right? Okay, so principle of work and energy, right? When the change in kinetic energy from position 1 to 2, the difference between the kinetic energy was equal to the total work done by the external forces, right? So these formulae also apply in rigid body kinetics, right? So this is the change in kinetic energy of the system, right? And we go back to using the same shorthands. KE is kinetic energy, PE is potential energy, right? And here, that is the total work done by external forces. All right. And when you have only conservative forces that are doing work, right? There's nothing, basically when there's no friction, right? You have conservation of energy. And again, the same principle applies, right? The nuances lie in how these terms change when we're looking at rigid body motion, right? So to just put a cap on that, this term is equal to the kinetic energy. So that's the T's. Right? We'd also said that that was shorthand KE. And then this term here, that is your potential energy. Right? PE. And the most common potential energies that you see are the potential energy, due to gravity, and the elastic potential energy that you see due to springs or those bungee cord kind of springs, right? For springs, you got to realize both when they compress and when they extend, you're going to have potential energy half kx squared, right? But for those bungee cords, only when they extend, because when they become shorter, they're not taut, so they don't store any energy. All right, those are things that you need to remember. So now when we get into the nuances of rigid body kinetics, looking at what's happening with rigid body, right? Let's look at what, we're going to break it down. We're going to look at the work done first, then we look at the kinetic energies, and then we look at the potential energies. All right. So, for example, if a rigid body moves from one position to another along a particular path, right, and that motion is caused by a force F that's acting on the body, right, the change in the work done by that force is the same thing which we'd seen if it was just a particle that was moving from point S1 to point S2, right? So you have the work done by the force to move from position 1 to position 2 is whatever your, you could do this vectorially, right? R1 to R2 by selecting a particular point, F dot dr like that, or you could write this as a scalar quantity as well, right? You're going from position 1 to position 2, and whatever the angle ends up being between your path, right? So F cosine theta ds, like that, right? In essence, all of this is just to say that particle work done on a particle and work done on a rigid body by a force, which is just causes pure translation, exactly the same, right? So the work done terms remain the same. Where new stuff comes in is what's the new thing that's happening when we're looking at rigid bodies, right? Things are rotating. So when the rotation comes in, right? So for example, over here, you have the initial position for this rigid body, which is the dotted position over here, right? You establish some kind of datum, right? So let's say you establish some kind of datum. There's an external moment. Obviously, a moment is what's going to cause the rotation, right? And that angle is basically changing from θ1 to θ2. All right. So for this case, where you have pure rotation, there's a moment that's acting on the body, and the angle it's rotating about this point here. Let's just, whatever this point could be, the mass center, need not be the mass center, whatever, just call it a random point P over there, right? The work done by this moment to change it from position 1 to position 2 is just equal to the change. You're just integrating over the angle now. And the good thing about moments are that they have the same units as energy, right? So you're just multiplying it by the change in angle that you have over here. Or you could have the scalar quantity as well, θ1 to θ2, m d theta, like that. And similarly to when you see work done by a force, if your moment is constant, right? The work done by that moment is just equal to that scalar quantity of the moment times the change in angle that you're looking at. All right. Now, when you're looking at, the work done by a force, the signage is a little bit more intuitive, right? Because you have a force, if it's moving in the same direction, then that work done is positive, right? But when you're looking at moments, right, you have to be careful, right? So it's positive, right? And when I'm saying positive today, going forward, I'm going to use this plus symbol. All right. What that means is that your moment and the change in angle have the same sense of direction. And this is when you're looking at rotating bodies, right? So you're always looking at planar stuff, and you're using your right-hand rule to figure out where is it going to be positive k hat or negative k hat, right? So if the k hat's in the same direction, then the work done is positive. So have the same sense of direction, right? And it's negative, which is going to be this minus sign over here when m and theta have opposite sense of direction. All right. So this is the important thing when you need to realize work done by a force in translation, same thing. Work done by a moment in rotation, these are the terms that are coming into the picture over here. All right. You need to remember this going forward in your engineering careers. But again, there's no homework problem on this either, and there's no exam problem on this concept either. All right. But you just need to be careful. You need to, impart this into your brain. All right. Any questions, guys? If you guys are taking notes, can I move on to the next page?
Yeah, I'm good.
I'm good.
All right. So next, now this is the super important thing, all right, that we're going to be testing you guys on. The kinetic energy of a rigid body. All right, so what's happening in rigid body motion? You have translation and you have rotation. Like when we were looking at the forces and we were taking our IG alpha terms and our MAVG terms for translation, for rotation and translation respectively, we do the exact same thing for the kinetic energy. All right, for a body that is there in pure general plane motion, what that means is that it's both translating and rotating, like you have over here, right? It's translating with a velocity vg, and it's rotating with a velocity, with an angular velocity omega, right? And this omega, the rotation could be about any point, right? It need not be about the point g. So the kinetic energy of this system here, you have a term for your translation, which is the same as what you have for train of thought for particle motion, right? So it's half mvg squared plus, now the term that comes in for rotation is half ig omega squared. The thing to remember here is that your ig, always take it about your mass center, similar to how when you're taking the translation and acceleration, when you were taking the acceleration and the angular acceleration, right? Ig alpha and mag, right? You always find out the acceleration about the mass center and the rotational moment of inertia about the mass center. It's the same thing over here. Other thing to remember, all scalar quantities in here. All right. So when you're looking at your work energy problems, you're going to have to see the same kind of thing, right? All right. When I was looking at the work, when I was looking at the kinetics, when I was looking at the forces and the moments, we had to look at the kinematics to find out a bunch of unknowns, right? Similarly, for work energy, you're going to have to do the same thing. The problem will be fully described in one position, and you will have to find out what's happening in another position. All right. And there you have to, always we solve everything vectorially, but when you plug things into this expression, make sure you convert those into scalar quantities. What I mean by that is, if you find out your VG and they have I hat and J hat components, make sure you can convert that into a scalar quantity, right? By taking the square root of the squared of the X component and the squared of the Y component. All right.
Yeah, absolute value.
Absolute value or magnitude, right? The same thing, right? So scalar quantity. All right. Now, few things to note over here is the simplest thing to note is that when you have pure translation, the kinetic energy of your body is just equal to half mvg squared. All right. When you have a rotation about a fixed axis, it's only rotation, and it's easy to look at it like that. What you can do is you can just find out whatever your moment of inertia. So this is a fixed axis, let's say about point O. Whatever the moment of inertia about the axis passing through that point is, times omega squared. And where are we leading into? For general plane motion, you could do one of two things, and this is up to you. Typically, you just use it's the first expression, right? So it's just half mvg squared plus half ig times omega squared. Or you could also find out the mass moment of inertia, the rotational moment of inertia, sorry, about your instantaneous center of rotation, and do omega squared over there, right? Here, that is your instantaneous center, center of rotation. Now, the iffy thing about doing the instantaneous center of rotation is, because you have to do energy conservation at two different positions, your instantaneous center of rotation could be different, right? So just be careful when you're using this. My advice would be to just use the general plane motion expression, just go with that, all right? But again, you can use the instantaneous center of rotation as well. All right, so before we move on to potential energy, any questions, guys? All good? Just remember, you have your IG omega squared term, half IG omega squared term. That's it. All right. That's the only special thing that's coming into the picture here. Gravitational potential energy, same thing as you have for particle motion, right? So you have gravity, which is acting downwards, right? You're changing. You have to select a datum, right? And you have, if you go above the datum, your energy is going to be positive. And if you go below the datum, your energy is going to be negative. So the expression is exactly the same. It's just equal to the weight times whatever the height is, right? So you could also say that this is equal to mgy like that, right? And this is positive if it's above the datum, and it's negative if it's below your datum. All right. And the choice of datum is arbitrary, as we saw in energy conservation. Just make sure it's consistent between your two positions, and the signs take care of themselves. All right, just don't choose one datum for one position and another datum for another position. Choose one datum and stick with it for the whole problem. All right, that's the exact same thing when we're looking at rigid body motion, particle energy. All right, finally, elastic potential energy is also the exact same thing as when we were looking at particles for your springs, right? So for example, you could have, a position where your extension of your spring is equal to 0, and it could compress or it could extend, right? Compression, obviously the displacement is negative, but your kinetic energy, or your potential energy, will always come out to be positive, right? Because it's just equal to half kx squared. All right, mechanical engineers, springs, FE exam, you need to, I saw from the last exam that many of you are not familiar with this. Become extremely familiar with this term. Force due to a spring is equal to k, sorry, not half, k times x, which is k times the extension. The potential energy due to a spring is equal to half times k x squared. All right, and this term here is always positive. All right, no matter if your spring compresses or it extends, because even if x is negative, you're taking the square of it, your negative sign goes away. All right, questions, guys? Straightforward stuff.
Yeah.
All right, move on to the next page.
I'm good.
Okay. Your right.
So just real quick, and
Yep.
maybe you already talked about this and I'm behind, but your potential energy sign, is that a V?
Yeah, V, capital V.
Okay. I thought we were using well, okay.
No, potential energy is capital V, and capital U is work done due to force. Hey, don't blame me. That's the authors of the textbook, and I've just been going along for the ride. So yeah.
I mean, is that standard, or is that?
We've been using capital V for potential energy in our course.
I know we have, but I'm talking about everywhere.
Hey man, physicists do their own thing. I don't know.
I had a quick question.
Yes, please.
So if you are coming from a point B above the datum
Mhm.
and go to a lower point but still above the datum, would the potential energy be positive because
Yes, it
you're
would
still
be.
above the datum? Okay.
Absolutely. So if you go, this is your datum, and this is your position 1, and this is your position 2. In both these cases, it's positive, right? So this is going to be mgy1 here, and it's going to be mgy2 over here. Absolutely. Yeah.
Thank you.
Just make sure it's consistent. For both of these positions, your datum is at the same line. All right. And finally, we move on to impulse and momentum, right? So to recall the things that we looked at when we looked at particle motion, linear momentum, vector quantity, body is moving, it's just equal to mass times the velocity as a vector quantity. That is your linear momentum. All right. Angular momentum, we looked at it very, very holistically, but I've kind of simplified it for you over here. If you're looking at just the plane in which your motion is happening. So for example, because we're only, for rigid body stuff, we're only concerned with planar motion, right? So if you're looking at just the plane, so this is the top view looking onto the plane, right? You always find your angular momentum about a point, right? So you have the linear momentum of a particle which is moving. Then what you do is you find out the shortest distance to the line of action of your vector, right? And then your scalar quantity for your angular momentum is just equal to your mv, your whatever your scalar quantity for the velocity is, times that shortest perpendicular distance, right? Also, you could do it vectorially, right? So if we look at it from the side, whereby now you're looking at the plane where the z-axis is going up, right? I hope this drawing makes sense. mv is on the xy plane. In that case, all you need to find is a vector from the point about which you're trying to find your momentum onto the line of action of your linear momentum. It could be, R could be like that, R could be like that, R could be like that. As long as it's going from that point onto the line of action, it doesn't matter how you select your vector R, right? And then you basically get your angular momentum is going to equal R crossed with mv, right? And that is always going to give you, right-hand rule, a direction which is perpendicular to the plane containing mv and R, right? That's just from the definition of cross products, right? So here, HP is just equal to R crossed with MV, like that, right? And the thing to remember here is that this is just a position vector from P, that's the point about which you're trying to find your angular momentum, to the line of action of MV. All right, and you can go on to any point. All right, so this is just a quick recall of what we looked at in particle kinetics. Yes, someone had a question? All right. Then for rigid body planar motion, we just break it down further, right? So when you have rigid body motion, planar motion, it's both translating and rotating, right? So you can say that your linear momentum is equal to, same thing, right? As a vector, it can just be m times the vg vector, right? Or you could also find your components in your x and y, right? So you have vgx, the scalar components, and vgy like that, right? So you could say that your x component of your linear momentum is just equal to m times vgx, and the y component of your linear momentum is just equal to m times vgy. All right. Because we're looking at planar motion of rigid bodies, you guys only need to be concerned with the angular momentum as scalar quantities, because the angular momentum is always going to be along, in the k hat direction out of the plane, right? So what we do is we find out the angular momentum about the mass center, and this is the most traditional way to do it, is always to do it about the mass center, right? And that angular momentum is just equal to Ig times omega. All right, or you could do it about a random point P as well. In that case, you're going to have to break it up, right? Either you find out the angular momentum about that point, the rotational moment of inertia about that point, or you can find out the angular momentum about the mass center. And then what is angular momentum? When you're looking at linear momentum, angular momentum is the moment of the momentum, right? So you're going to have for that p hat component, right? So if I'd actually drawn my p was right there, right? So you're going to have a certain distance to VGX, so let's call that dy, and then you're going to have a certain distance to VGY, so let's call that dx, right? So the moment of the momentum for VGX is going to be for VGX, is it going to be, it's going to be negative, right? So you'll have minus m VGX times dy, and then for VGY as well, it's going to be negative. So you'll have minus, but just be careful of how you, for this particular case, it's negative, right? Because both of them are coming out to be negative, but for your, whenever you're solving your problem, just make sure you're doing your cross products correctly, right? So you're gonna have MVGY times dx. All right, then further breaking that up, if you look at pure translation, all right, your Hg is going to be 0. That's your angular momentum is going to be 0. Or you could have rotation about a fixed axis. Right, we can say H naught, that's equal to I naught omega, whereby your fixed axis is this point, is passing through this point O, right? So that O there is your center of rotation. Or for general plane motion, instead of using this expression here, as we've said before, you can find out the instantaneous center of rotation. Say that that's just equal to whatever your rotational moment of inertia is about that instantaneous center of rotation times omega. Right, so here you have the instantaneous center of rotation. All right, questions, guys?
So rotation about a fixed axis, is it same no matter where it is on an
Yes.
axis?
But you just have to find out your rotational moment of inertia about that axis. Yep. IO, it's going to be different from IG, right? Because IG might not be the axis about which you're rotating.
All right.
All right, move on. Good.
Yeah.
Okay, and then finally, we've got our concepts of impulse and momentum, right? Which is exactly the same thing, right? So for your linear impulse and momentum, right? Your initial momentum plus whatever impulse is imparted by your external forces is equal to your final momentum. And then the same thing applies for your angular impulse and momentum. Again, I'm using scalar quantities over here because planar motion, it's always about the k hat direction, so it doesn't matter, right? So it's your initial angular momentum plus your angular impulse due to the moments that are acting on the body. That's equal to your final angular momentum. All right. So when you're writing this vector expression here is going to give you 2 equations. This expression here is going to give you 1 expression, right? Everything's in the k hat direction. So you get 3 scalar equations, right? So you can write those out. So you get mvg x at position 1 plus, and then whatever is your impulse of the forces in that direction. So fx dt, and that's equal to m times vgx in position 2. Similarly, you get m times vgy. So now you're looking in the y direction in position 1, plus your impulse due to all the forces acting in the y direction. That's equal to m times vgy 2. All right, and similarly, for your angular momentum, pick a point. You can't pick multiple points. You can only get 1 moment equation, right? Remember, this is what we learned in statics. Seems like eons ago, right? So your angular momentum in position 1 plus your angular impulse due to all the moments that are acting on the body about that point P. is equal to your final angular momentum. All right, so this is true for a single body, or it also applies to a system of rigid bodies. Similarly, as we'd seen with a system of particles. Right? Now, with rigid body motion, some cool stuff starts happening. And what we're going to do is, again, although we're not testing you on the exam, I'm going to show you guys some demos on Tuesdays. And I'd said that we're going to have you guys come in person, but just with the number of cases that are rising in Maine, I don't think that's a good idea. So I'll just do a couple of demos live on Zoom, and hopefully they're not too bad, right? So when you're looking at conservation of momentum, right, if there's no external linear impulse, then your sum of moments in position one, your linear momentum in position one is equal to your linear momentum in position two, right? And if there's no external angular impulse, and this is the cool expression, that means that your angular momentum in position one is equal to your angular momentum in position two, or your term, whatever your rotation is happening, IO omega remains constant. There's a very cool demo. Let's see if I can try to do it for you guys over here. It's probably not. It's going to be a radical fail, but let's try it nonetheless. What it is when you're rotating and you see like what are those? The figure skaters, right? When they have their arms out, their rotational moment of inertia is high, so the speed at which they're rotating is lower, and when they bring their arms in, their the rotational moment of inertia decreases, and their angular velocity ends up increasing, and that is because of the conservation of angular momentum. So let's see if I can do this. So I'm going to start off with my arms out, and then you should see me speeding up. Let's see if this works. All right, that was terrible. That didn't work, but we're going to do a better job on Tuesday when we take a look at it. Trust me, it works. It's awesome. All right. Okay. All right. With that, do you guys have any questions? We should move on to our two problems that we want to do before we call it a day. Also, if you guys have heard of the gyroscopic effect and things like that, that's also due to angular momentum. I'll show you guys that on Tuesday. Good? All right, give me a second. All right, you guys are gonna have to give me a second. I think I forgot to do something here. All right, so